Deep dive into Snowflake architecture now. When Snowflake was founded, there were a couple of traditional architectures prevalent in the data platform industry. There was a shared storage architecture and a shared nothing architecture. These architectures had a very tight coupling of compute, storage, and services of databases. The shared storage architecture was predominantly being adopted by OLTPs in the RDMS world. This allowed a number of servers to connect to a common centralized disk storage. Now, this architecture had issues of scale, performance, and cost because there were limits to how many servers we could add in this architecture. The disk storage was expensive, it had performance contentions, and there were limits to how many nodes we could just add to the same common centralized storage. On the other hand, shared nothing architecture allowed to distribute data across multiple compute nodes on a cheaper disk storage. This was being adopted by typical MPP based data warehouses or Hadoop architecture. And we also see NoSQL databases adopting this architecture. Now, in this case, since we were able to distribute data across all the nodes, it allowed us to remove some of the performance and scalability constraints. But then, because of the number of nodes required, it started getting into complexity, management, and elasticity issues. Now, both these architectures were also constrained to a single cluster. A set of data was owned by one cluster, and that caused issues around isolating workloads, concurrency, and elasticity. Since everything was owned by a single cluster, it was not possible to provide dedicated resources for different workloads. Also, when we needed to add more resources, it required time and extra work because data had to be rebalanced. Now, at the same time, cloud services in the public cloud were becoming prominent, and Snowflake founders saw the opportunity to adopt a cloud native architecture and solve these constraints from a traditional data platform world. They came up with this multi-cluster shared data architecture, which used a centralized cloud object storage, and a number of clusters could connect to the same cloud storage and operate on the same data. There was a services layer which coordinated and allowed all these clusters to work together on the common data sets. Now, this removed the bottlenecks of both the architectures we discussed previously. Because the compute essentially became stateless, we could instantly add compute, remove compute, start or stop the compute. They were all operating on the same data set, so it was possible to instantly add more resources or remove resources operating on the same data. So performance, concurrency, different workload did not have an issue. We could dedicate resources to different workloads as well. So on one side, this architecture decoupled these three layers of storage, compute, and services, but it also logically integrated and offered them in a single platform. So this removed the constraints being offered by traditional data warehouses and Hadoops of the world in those days. Let's now look deeper into each of these layers. Let's look at the storage layer first. Now, when we are storing data into Snowflake Cloud Storage and data being sent by any of the data sources, Snowflake optimizes this data automatically in its internal format, compresses it, columnarizes it, and also encrypts it automatically. Now, Snowflake has also started to offer an option where you could make use of your own cloud storage buckets and keep data in open table formats in Iceberg. In that case, the files are in Parquet format, which are columnarized and compressed, and metadata is collected to make the queries perform more efficiently. The encryption comes from your own side. You can have your own encryption at the storage layer. So those are the two storage options which Snowflake offers. Now, with this interoperable storage, you could have any types of data, structured, semi-structured, and unstructured, and all different data types being stored in the same common storage layer. The second layer in this architecture is elastic compute layer. The work of this layer is to perform various functions to perform inside this data platform. For example, bringing the data inside it, taking the data outside, performing various analytical queries, running different data transformation or data engineering pipeline functions, running machine learning model work like scoring and training the models. These computes could run multiple languages like SQL, Python, Java, or Scala.